Why is the suction limit 32 feet and is it related to the 32 feet s squared? If you stick a suction hose in a well to lift water, you can lift it a maximum of 32 feet before gravity breaks the column of water, no matter how big the pump is. In other words, when you drink with a drinking straw, that works until your straw exceeds 32 feet, then it no longer works. Why? And is that related to 32 feet sec too? Because you're not really sucking anything up anything. The outside pressure is pushing it from the outside. At sea level, 33 feet is as high as the atmosphere can push water up into a vacuum. Doesn't matter how thin or thick the space is, either. ULMXPFTW gave the physics answer the right answer, but from an engineering perspective you can pump water higher than 32 feet. How many cities have a water tower shorter than 32 feet? But you do it by increasing the pressure of the water at the base. You can do that directly, for example with a syringe-style pump. You can also do it indirectly, for example by putting water in a sealed container and pumping compressed air into the same container. Then the container is at, say 100 pounds per square inch instead of atmospheric pressure 14.7 pounds per square inch, and you could pump it about 7x higher. Let's assume a perfect vacuum, and let's use Bernoulli's equation. If we simplify a bit, we'll get P1 rho xg(h). P1 is atmospheric pressure, rho is 1000 kilograms m3, g is 9.81 meters s2. Plug that all in and solve for h, and we get h max as 10.32 meters, or 33 feet, 10 inches. Now we won't be able to recreate a perfect vacuum, but we can get close, resulting in somewhere around 32 feet. Because a hard vacuum 0 atm is 1 atm relative to ambient, and that 1 atm 14.696 pounds per square inch pound in 14.696 pounds of water has a volume of 387.5186666 in divide by 1 in 2 per inch 2, and you get 387.5186666 in, or 32 feet, 3 and 33/64 inches. It's not directly related to Earth's gravity 32 feet s, but they do have a linear relationship, since the weight of water is dependent on local gravity.